Okay, hello, welcome to my channel. Today we're gonna continue from last lesson and we're gonna expand the Schrodinger equation to get the general form of the Schrodinger equation, and then we're gonna talk some about the commutations of operators, and I would like to give you a very interesting example later on about like operators and commutation and stuff. So let's get started with the general Schrodinger equation. So you remember last time we considered a particle with no potential, so it is free in a plane, it's just there. But today we're gonna consider a potential there. So suppose you have a potential that is a function of x and t, so Vx and t. So your energy now would be the kinetic energy plus the potential energy. Hence, E would equal to T plus V. And you put a hat on it, put it in the operator form. So you would have your E hat would equal to T hat plus V hat. And this guy, like as we learned before, this T hat is equal to minus h bar squared over 2m, the second order differential. And V is just V of x and t. Yeah, it's just that. And the E hat here in quantum mechanics, we call it Hamiltonian. And instead of writing it as E hat, we would write it as, okay, I would write it as here, Hamiltonian. This is H, as some people put a hat and some don't, but I would just put a hat there for now. So, as you remember from last lesson, also, the free Schrodinger equation has a time dependence part and an energy part, and the full Schrodinger equation is basically the same. You would start with the time dependence part. This would equal to h psi. H psi, as you know, would be h bar over 2m d squared dx plus v of x and t psi. Alright, that's it. That is the full Schrodinger equation. Pretty nice. Alright, so let's continue to the operators and commutation. So first, I would want to remind you of these guys. So we mentioned p hat before in the last lesson, but we didn't mention x hat. So with x hat, if it acts on a function of x, you would get back x times the function. And with p, when you act on a function of x, it would equal to this. So some might question that what if it's like a function of p, for example? What if you got that? Well, I just want to mention this earlier, as we might or might not visit this later. You would have p hat on a function of p would be the same as x hat on a function of x. It would be p on psi p. And with x, it would kind of look like the p function on here, but not quite. It would be ddp psi p. Yep, I just want to mention this early on first. And from that, we can say that when you're dealing with like operators acting on functions, well, the order matters, all right? The order. matters. As we will see right here in the next example, consideration, whatever. So when you have this guy is completely different from this guy. So this would not use you 0 at all. That's just wrong to assume that. So we know that these two guys are different. So let's expand those. You would kind of start with this. P would be acting on psi first. Then after that, X would be acting on psi later. And this is the same for this guy. Instead, X will be acting first because it is standing in the front. And you expand this. H bar I X psi P of X psi. Alright, there's a number, you can pull it out, whatever. Yeah, you can put this in, this part out. This in would get you psi, continue to that up. Okay, yep, you can actually, yep, that is correct. We also have like another table here, so I'll just write it briefly as this would be equal to IH bar on psi. The expansion itself is not hard, but it might be confusing to do it for the first or second time. It is still confusing for me to do it because I don't know why. But ultimately, you would get IH bar on psi from this thing. And if you remember, I mentioned it before, like commutation of A and B would be equal to AB minus BA. And you can see AB minus BA on a function. So you can say that IH bar is equal to this. Yep. Like that. So this is actually a quite fascinating solution to get, because when okay, let me draw out the board to compare these. So quantum world, we have operator, a wave function, and eigenstate. Well, maybe you noticed this when I mentioned eigenstate, but these guys are actually very close to their linear algebra counterpart, which is, well, operator would be a matrix. Wave function would be vectors. Hence, when you get an eigenstate, some people call them like eigenvectors and stuff. So these are like vectors. Eigenstates, of course, these guys are eigenvectors. So this is kind of like a double-edged sword. It is easy to understand, but also kind of hard in a way. It really depends on like the person you ask. And next, we're gonna move on to an example of operator commutation. So example. So we're gonna consider something called Pauli matrix, like Pauli matrices, and these you would be learning about them later in the course. Well, not now, maybe like second year, probably. So like when you learn about spin, you're gonna see these guys first, and these are like very fundamental, very important. So you would have these are sigma, either 1 or x. I would be writing 1. So the 1 is here. the one is like, okay, I don't know if I want to talk about that now, but there's a very easy way to remember these. So one would be 0, 1, 1, 0. 2 would be the y one, so you know this guy is imaginary. 0 minus I 0. And 3 is 1 and minus 1. Minus 1. Yep. So you have these. And when you do the commutation of, like, say, 1 and 2, what you get? Well, let's just expand these. This is 1, 2 minus 2, 1. 1. So let's compute on these. So 1 and 2 would be 0, 1, 1, 0. 0 minus I. 0. Or to be quicker, I'm just gonna look at the answer. This is I. 0, 0 minus I. And the other guy is 2, 1. Yeah, so remember the order matters. So these would not be the same. Oh. That is minus I first. Yep. And when you put it back, you would get 2 I. 0, 0 minus I. This is, well, you factor the I out, you get 1, 0, 0 minus 1. This is 2I sigma 3. Yep. You compute, you put two matrices in a commutation and you get back another matrix. Well, that's normal. But here, you put in two operators, which are basically matrices, but you get back a number. That's why I'm telling you that, like, this guy is, like, very special, and this guy is, well, normal. You can say this obeys the rule, but that guy, to prove it, is very complicated. So we just have to accept that it is like this. Okay, so that would be the end for today's. That would be the end for today. Goodbye.